At this point, we are ready to start Chapter 4 with the second and last group of slides that we have for Chapter 4. And in it, we're going to talk about, among other things, the law of large numbers. And let's start out by illustrating something that will be clearer as we get a little further along. It's called the Gamblers Fallacy. It's the mistaken belief that if you have a streak of bad luck, that means you're going to be due for a streak of good luck. Let's say you're playing a coin toss game in which you win $1 for heads and you lose $1 for tails. After 100 tosses, you're $10 in the hole, maybe, because you flipped 45 heads and 55 tails. The empirical probability, which we'll talk a little bit more about also later, the historical probability is 45% for heads. Even though you have a 50-50 chance of rolling heads, when you did it, in this particular instance, you only got 45 heads. So if you flip longer, if you keep playing the game longer, when you get to 1,000 tosses, maybe you're out of 1,000 tosses, you get 490 heads and 510 tails. You have brought the empirical ratio, the historical ratio, up to 0.49, almost 50%, but you're still $20 in the hole at this point. You know the law of average helps you, that eventual theoretical probability is 50%, so you decide to play the game a little more. The truth is that chances are, even as the game continues, and even if the probability increases from the 49 to 50, you're not going to get even. When we talk about counting in probability, we talk about different things. If you were to make R selections from a group of n choices, how many different arrangements are possible? Here's an example. How many 7-number license plates are possible if they're all numbers? Here's a California plate. And you can see on the plate that there's 7 numbers. Each number could be a number between 0 and 9. 10 different possibilities. And if you were going to come up with unique numbers, no two numbers the same, using those 7 numbers, you could get 10 choices for each one of the 7 numbers. In order to calculate the number of different choices, it would be 10 times 10 times 10 all the way up to 10 times 7, 10 to the 7th power. 10 to the 7th power would give you 10 million different possible license plates. Now, another way to call this or identify this, it's a permutation, because the order of the numbers that you create matters. Okay, so if you wanted to know how many permutations you could get out of those 7 numbers, that there would be 10 million different license plates that were possible. When we have formulas about those, we use factorial numbers. A factorial number is a number followed by an exclamation point, which means that if you were looking at factorial 3, it would be written as 3 exclamation point, and that would stand for 3 times 2 times 1, so that factorial 3 would be equal to 6. If, by the way, you see factorial 0, that is also a number equal to 1. A permutation, as I said in the previous slide, is arrangement of objects in a specific order. What's important to know is that the actual order matters. The manual formula for calculating the number of permutations that are possible is on the bottom left of your screen. N factorial divided by n minus r factorial. Let's talk about what that might mean. We're going to have examples of that later when we go through the instructional videos. If you wanted to know how many permutations you could get if you wanted groups of 3 taken out of a possible list of 5, to create the formula for that on the top of the fraction, the numerator would be 5 times 4 times 3 times 2 times 1. The denominator would be 5 minus 3, which is 2 factorial, so that would be 2 times 1. So what you would have is 5 times 2 times 5 times 4 times 3 times 2 times 1 on the top, and then 2 times 1 on the bottom. And then you would manually do that calculation to get the answer. Or, hopefully, you would just turn to the Excel function, and the Excel function would be equal PERMUT. And then when you did that, and again, you'll see some samples of this when we get into the instructional videos, you would just have to enter number as 5, and that you wanted groups of 3, so it would equal PERMUT, parentheses 5, comma 3, and then when you hit the enter key, you would have the answer. Combinations, on the other hand, the order that you choose items doesn't matter. And the formula for that, for combinations, is similar to that for permutations. And first of all, how it's designated. If we wanted to know about combinations of 3 that we could get out of 5, we would write that as equal, or combinations would be 5, small n would be 5, large C, and then number would be 3, and on the top we would have 5 times 4 times 3 times 2 times 1. The bottom would be n minus 3, 5 minus 3 is 2, so it would be 2 times 1, and then r, which is 3, would be times 3 times 2 times 1. What that's telling you is you get a lot less combinations when the order doesn't matter than you do permutations. Or you could use the Excel function equal COMBIN, which is much easier. Again, you'll see some examples of this when we actually go through and work these out for you in the instructional videos. Here's a real case. A business owner has a choice of 5 locations in which to establish her business. She decides to rank each location according to certain criteria: price of the store, parking facilities, whatever. How many different ways can she rank the 5 locations? So we've got 5 times 4 times 3 times 2 times 1. Excuse me. In doing the math, we would come up with 120 different ways to rank these locations. Using factorials, it would be factorial 5, which tells us it's 5 times 4 times 3 times 2 times 1. Or if we wanted to use the Excel function permutations, it would be written as 5 permutation P. Want to rank all 5, and we would enter that into the Excel function on your iPad. It would return 120. Suppose the business owner will only wish to rank the top 3 of the 5 locations. So how many different ways can she do that? Well, that would be 5 times 4 times 3, or 60 different ways to rank these locations. If you wanted to use the permutations designation, it would be 5, large P, small 3, and it would equal 60. if you entered it into the permutations function in Excel. When we talk about probability and counting rules, they can be combined together to solve many types of probability problems. When you use the fundamental counting rule, the permutation rules, and the combination rule, you can compute the probability of outcomes of many experiments, such as getting a full house when 5 cards are dealt, selecting a committee of 3 women and 2 men from a club consisting of 10 women and 10 men, or other things like that. And as we showed you before, probability is a number always between 0 and 1, or 0% and 100%. The closer the probability is to 0, the less likely the event is to occur. The closer the event is to 100%, the most likely the event is to occur. When you're working on problems in this, here is a pivot table that you might use that summarizes a bunch of listings that the Cooper Realty Company has. And you can see along the left-hand column, you have the value of the properties. Under 150,000, 150 to 199,000, and so on. And then along the top, you can see how long these properties have been on the market. Under 30 days, 31 to 90, over 90, and then the total. So now if you were to answer a question about this, given that a property is on the market for under 30 days, what's the probability that the asking price is between 200 and 250,000? Well, what do you have here? Total number of properties that have been on the market for under 30 days is 100 properties. So we're going to create a fraction, and the total of the number being considered goes as the denominator. We're considering only the properties on the market under 30 days. There's 100 of them. Of the 100, how many has an asking price between 200 and 250? And you can see that answer is 20. So we have a fraction now, which is 20 over 100, 20%, or 0.2 if we were going to look at it as a decimal. What's the probability that a randomly selected listing has been on the market for under 90 days? When we say a randomly selected market, that means all the properties are under consideration. So the denominator of our fraction is now going to be 800 because we're considering all of them. Of the 800 properties, how many have been on the market for 90 days? Well, that would be the sum of the 100, which puts under 30, and the 500 that have been on 31 to 90. So our fraction would look like 600 over 800, and we would solve that to come up with the answer. If a property has been on the market over 90 days, what's the probability that the asking price is between 200 and 250? Well, how many have been on the market for over 90 days? 200. Of those 200, how many have an asking price of 200 to 250? That's 100. So all you need to remember is to be careful when you're viewing a table like this, to select the columns or some of the columns that represent the question you're being asked. When you do that and then set this up as a fraction, the solution to all of these is really very straightforward and very easy. This is a contingency table or a pivot table. Shows frequencies for 2 qualitative or categorical variables actually, X and Y. And this is comparing exercise gear from Under Armour, Nike, and Adidas. And the calculation is dividing the people that buy these products to those that are under 35 and those that are over 35 on the second line. And if then you want to do calculations on this, you're able to do so. Here, X is age group with 2 outcomes, and Y is brand name with 3 outcomes. And using this, you're able to do calculations that address things that fall into those 2 categories. For example, if you wanted to know out of the under 35 group, what's the probability that somebody buying exercise gear is going to buy Adidas? So first thing you would need to do is to total the under 35 group by adding 174, 132, and 90, and that total would be the denominator of the fraction. 90, on the other hand, would be the numerator. And when you did that math, the decimal you would get would equal the decimal equivalent for those under 35 that are most likely to buy Adidas. Again, when we look at some actual examples in the instructional video, it'll become a little clearer to you. When you're assigning probabilities, there's really 3 ways to do it. The classical method, that's based on the math. You flip a coin, you get a 50-50 chance it's going to be heads or tails. And that doesn't mean it'll always be 50% heads and 50% tails. But as we've looked at earlier on, if you do it enough times, the classical method will eventually appear to be happening. It'll get closer and closer to the classical method. The relative frequency method is based on history or your experimentation of history. And again, we'll go back to the empirical terminology that we looked at earlier on. We flipped the coin. At first, we got 45% heads. We kept flipping the coin, and we ended up getting 49% heads. This is the relative frequency method, and would be signified or detailed for us if we did a frequency chart on whatever it is that we're doing. And the subjective method, that's the one we all use all the time. That would be how when we assign probabilities based on our opinion or our judgment. Or, as I like to say, and statisticians don't like, is you're making a wild-ass guess at what's going to happen. An experiment in its sample space. An experiment is any process that generates well-defined outcomes. The sample space for an experiment is the set of all the experimental outcomes. An experimental outcome is also called a sample point. Probability can be defined as the chance of an event occurring. It can be used to quantify what the odds are that a specific event will occur. Some examples of how probability is used every day would be weather forecasting, like 75% chance of snow or rain, or for setting insurance rates. A probability experiment is a chance process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. A sample space is the set of all the possible outcomes of a probability experiment. An event consists of the outcomes. So if you toss a coin, the sample space is heads or tails. If you roll a die, the sample space is 1, 2, 3, 4, 5, or 6. If you answer a true-false question, it's either true or false. If you toss 2 coins, you can get heads, 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 tails, tails, heads, tails, tails. Those are all of the choices that are available. Heads, 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 tails, tail, heads, tails, tails. There are three basic interpretations of probability. The classical method, which is theoretical, and an empirical probability is based on observations or experiments. You flip the coin like we just said earlier 100 times, you got 45 heads and 55 tails. And so that's what empirical or historical probability is. On the other hand, if you have these aha moments, a subjective probability is an estimate based on experience or intuition. You think something is going to happen for one reason or another that is not based on established fact. So when you look now at the three types of probability, the classical or theoretical probability is the chance of rolling a 4 is 1 out of 6 if you're using a 6-sided die. Empirical probability could be that she's a 92% free throw shooter for the season, based on the fact maybe that this young lady had 100 free throws that she had to attempt, and she made 92 of them. So that, on a historical basis, that's what happened. In a subjective probability, there's a 70% chance that he or she's going to go out on a date with me, based on your infinite wisdom. A classical probability uses the sample spaces to determine that an event will happen and assumes that all outcomes in the sample space are equally likely to occur. And the formula is there, but we're going to try our best to simplify how you're going to do your calculation. If an experiment consists of a sequence of 2 steps, in which there are 4 possible results for the first step and 2 for the second, then the total number of experimental outcomes is 8. And how did we get that? Well, we multiplied 4 times 2. A helpful graphical representation of a multi-step experiment is a tree diagram. And you can use a tree diagram if you want to find the sample space for the gender of, as an example, 3 children in a family. A woman has a child, the first child, that's either going to be a boy or a girl. When she goes to have the second child, if she had a boy the first time, it's either going to be a boy or a girl the second time. If she had a girl the first time, it's either going to be a boy or a girl the second time. Now she has the third child, and the same rules apply. So if you look at this, what do you see? You see that there's 1, 2, 3, 4, 5, 6, 7, 8. 8 different possibilities. And how many of them are going to be, 2 boys and a girl? Any one of the combination that you want to attempt, you would be able to calculate, setting it up from this chart. When a single die is rolled, what's the probability of getting a number less than 7? Since all of the outcomes, 1 through 6, are less than 7, the probability of getting a 7 is certain. The probability of a number less than 7 is 6 out of 6, and that's going to equal 1, which is the maximum probability you can have. It's always a number between 0 and 1, or 0 and 100%. 2 events are mutually exclusive, but they cannot both occur at the same time. They have no outcomes in common. And we'll look at examples of that also. The corporate research and development centers for 3 local companies have the following number of employees: U.S. Steel 110, Alcoa 750, and Bayer Materials 250. If you select an employee at random, find the probability that the employee is employed by U.S. Steel and Alcoa. Well, you'd have to add up the number of employees, and when you do that, you would get 1,110. So of the 1,110, how many are working for U.S. Steel or Alcoa? 110 for one and 750 for the other. So you'd have a fraction 860 over 1110. which would be 86 over 111. That would be your probability. Another example, a recent survey asked 100 people if they thought women in the armed service should be permitted to participate in combat. There's the results. And so you could work out any problem from that if you wanted to know the probability that males were in favor of, if you selected a person at random, what would be the probability that that person would be a male in favor of a women being in combat. Well, there was 100 people totally. That's the denominator of the fraction. And of those 100 people, 32 of them are males who would like to see females in combat. So your fraction would be 32 over 100. A paint manufacturer wishes to manufacture several different paints, and the categories include a whole bunch of different colors, 2, 3, 4, 5, 6, 7. 2 different types, either latex or oil, and 4 different textures, and then 2 different uses, outdoor and indoor. How many different kinds of paint can be made if you select one from each one of the categories? If you wanted to have one in stock, and it would be simply multiplying these together. 7 times 2 times 3 times 2. And that would give you 84 different kinds of paint. Now we've covered a lot of area. It's going to be a lot easier when you look at these using the instructional videos. These slides were attempting actually to make you a little bit more familiar with what you're looking at, and hopefully you'll be comfortable doing your calculations using Excel.